Hey there, we're just swimming in information these days, right? Data is everywhere, and honestly, it can feel like a lot of noise. Well, what if there was a way to tune out that static and find the clear signals hidden inside? Today, we're going to pull back the curtain on the world of statistics and see how it helps us turn all that raw data into smart decisions. And that, right there, is the big question. How do we find those signals? And look, statistics isn't about memorizing scary formulas. Not at all. It's really just a method, a way of thinking that helps us find clarity. It's about spotting that one clear voice in a very crowded room. When you boil it all down, it's actually pretty simple. It's a process. First, you gather the information. Then, you dig in and figure out what story that information is telling you. And finally, you share that story with the world. That's it. It's the basic framework for making sense of, well, anything. Okay, so let's start our journey with the most straightforward kind of statistics, the stuff we can literally see and measure. This first act is all about describing the data you have right in front of you. Yeah, a good way to think about this is like you're painting a really detailed portrait of a small group. We're not trying to make any grand guesses about the rest of the world just yet. Nope. Our only job right now is to accurately and clearly describe the specific data points we've already collected. To make this feel a little less abstract, let's stick with one core example through this whole thing. Let's imagine we've developed a new drug for high blood pressure, and we test it on a group of 150 patients. We've measured how everyone's blood pressure changed. So, what do we do now?
Well, there are two big ways we can start to describe this group of 150 people. First, we ask, what was a typical result? We call that central tendency. And second, we ask, how much did the results vary from one person to the next? And that's what we call dispersion.
And this is where it gets super interesting. We all know the mean, right? That's just the average. But imagine one patient in our study has a completely wild reaction. Their blood pressure just plummets way more than anyone else's. That one person, that outlier, could drag the whole average down. The median, on the other hand, is just the value smack in the middle. It doesn't care about extremes, which makes it a much more stable or robust measure of what's typical. All right, so by using these tools, we've got this perfect, crystal clear snapshot of our 50 patients. We know the typical response, and we know how spread out the results were. But, and this is a big but, that's pretty much where descriptive statistics stops.
Okay, on to Act 2. And this, my friends, is where statistics gets really powerful. We're about to take what we learned from our small group and make a smart, educated guess about everybody. It's called the leap of inference.
I mean, this is the million-dollar question, isn't it? It's awesome that the drug seems to have worked for 150 patients. But a doctor needs to know if she can prescribe this to the millions of people out there with the same condition. How on earth can we know that? And that question brings us to a really, really important distinction. The sample is the small group we can actually study, our 150 patients. The population is the entire giant group we wish we could study, every single adult with high blood pressure. Since we can't test everyone, we have to use our sample to learn about the population. And that right there is the whole job of what we call inferential statistics. It's the set of tools that lets us build a bridge from the hard facts of our little group to a really good guess about the whole wide world. It's how we make the leap. So, how do we do it? Well, it's actually this really clever bit of reverse logic. We start by playing devil's advocate. We assume the exact opposite of what we're hoping to prove. We say, okay, let's assume our drug does absolutely nothing. That's our null hypothesis. Then we look at our data and ask, all right, if this drug really was useless, how weird are our results? How surprising is it that we saw this big of a change? Okay, so how do we actually put a number on that level of surprise? Well, that brings us to one of the most famous and maybe one of the most misunderstood ideas in all of science, the p-value. The p-value, I love this description, it's literally a surprise-o-meter. It's just a number between 0 and 1, and it tells you the exact probability of seeing your results if that null hypothesis, the one that says no effect, was actually true. So a really tiny p-value means your results would be incredibly surprising, practically a miracle if the drug did nothing. Which, of course, leads to the next big question. What's the cutoff point? How surprised do we need to be? How low does that p-value have to get before we can finally say, you know what? I don't believe that no effect idea anymore. I think this drug is actually doing something real. Well, in the scientific community, the standard answer is this number, 0.05, 5%. Think of it like the official line in the sand.
If your p-value is less than 0.05, it means there's less than a 5% chance you'd see results this strong just because of random luck. And when that happens, we get to call the results statistically significant. It's our green light to reject that no effect idea and conclude our drug probably works.
All right, time for our final act. Let's open up the Explorer's Toolkit. We understand the logic now, but what's the actual tool you use to calculate that all-important p-value?
And the thing is, the answer totally depends on what kind of question you're trying to answer and what kind of data you're working with. I mean, you wouldn't use a screwdriver to hammer a nail, right? It's the same in statistics. You have to pick the right test for the job.
In this table here, it really breaks down the basic choices for you. So if you're comparing averages between two groups, like our drug trial versus a placebo group, you'll probably use a t-test. If you want to see if two things are connected, like maybe age and blood pressure, you'd look for a correlation. And if you're dealing with categories, like counting how many men and women prefer different newspapers, you'd use a chi-square test.
So let's bring it all home. The really crucial point is this. Statistics isn't a crystal ball. It doesn't give us 100% certainty. What it does give us is a powerful framework for dealing with uncertainty. It helps us weigh the evidence and make the smartest possible decision, even when we don't have all the answers.
You know, this quote just sums up the whole idea perfectly. All it's saying is that if your data looks really, really weird based on your starting assumption, your no effect theory, then maybe your starting assumption was just wrong. The data is pointing you toward a different, more interesting story.
So whether you're talking about medicine or business or sports, the world is just overflowing with data, waiting for someone to ask the right questions.